So we ended the last recording by defining CMRR as the ratio of the differential gain to the common mode gain, and depending on whether the mismatch in RD causes common mode gain. Ideally, you want the common mode gain to be 0, right? But a mismatch in the RD or a mismatch in the GM can cause some value for ACM to show up. And then once you know the value of ACM or gain common mode, you can then plug it into the CMMR formula and get this. Okay. All right. So that's where we left it last time. And I have some problems that we'll get to later. One more topic, yeah, is on the BJT differential pair. Now we have seen 8.3 before, where I walked you through some of the basics of the BJT differential pair. Here what I've done is in one slide 46, I've tried to capture all the formulas related to BJT differential pair, including, how do you find the common mode range, common mode maximum and common mode minimum, large signal values. So these, I think we have, if you haven't seen before, they have MOS counterparts. Then for small signal values, there's a bunch of formulas again. I guess the important ones are these: the RID, which is this resistance looking into the circuit, is given by this formula. Then the voltage gain, VOD by VID, small signal, is GMRC, which we have seen before, same formula. But it can also be written as RC by RE plus RE, which has this summary total resistance in the collectors by total resistance in the emitters. There is a similar definition of CMRR in the case of BJTs as in the case of MOSFETs. So you take the ratio of the differential gain to the common mode gain. In our textbook, there's one reason for common mode gain, which is the variation in the collector resistances that's given. So you see the formula for common mode gain when only there is a difference in the collector resistance, and then you have the CMRR formula shown here at the bottom. So all this is summarized and the analysis is pretty much similar. I guess the big difference always is that there is a base current in BJT circuits, while there is no gate current in MOS circuits, so that adds some complication. There's an example from the textbook that if we have time, we'll come back to look at this. If not, I'll expect you to just go through it. It's a pretty simple exercise. It uses a lot of the formulas that you see below to find CMRR, common mode rejection ratio, for this circuit. Okay. All right. So with that, and we spent 5 minutes already, I'm going to go back and see where our first example numerical is on section 8.2. All right. So I think on slide 27. Okay. So we are at slide 27. We start with an exercise, which is from page 603. It's a pretty straightforward problem. It says there is a mass differential pair. It has a total current, biasing current of 0.8 milliamps. So you know that each one, each transistor has half of that. Transistor WL ratios are given as 100. The K parameters are given for the, and it's a N type NMOS device, so just N is required. The early voltage is given and the drain resistance is given. So given all this, find VOV, then find GM, RO, and AD. These are small signal parameters. VOV we know, anyway as required. So the formulas to use are, VOV, this comes from the current ID formula. GM is this, RO is this, AD is this. So pretty straightforward, I think, application of the formulas that we have talked about. And so here it is. ID is I by 2, which is 0.4, W by L is given. We know ID has this shape also, so VOV can be found to be 0.2. This is the circuit. GM is this formula, 4 milliamps per volt. RO is this formula. AD is this formula. Because RO is known, 50 kilo, 5 kilo and 50 kilo, they are in parallel, so that reduces the 5 kilo slightly. So you get this AD. Okay? So I think that's a straightforward example, but it's important to see how you use various formulas to find AD finally, the gain. And what was the gain? Let me look one more time. We got a pretty decent gain, I think, of about 18, which for a MOS amplifier is not bad. Okay, next we got problem 814. So it's required to design an NMOS differential amplifier to operate with a differential input voltage that can be as high as 1.1 volt. So 100 millivolts is the maximum. This has to happen while keeping the nonlinear term under the square root in equation 8.23 to a maximum of 0.04. So this value, which is in one of those formulas for, I think, current, has to be limited to 0.04. Go take a look at 8.23 and you'll see this shows up. So this has to be limited to 0.04. Also, transconductance GM has to be 2 milliamps per volt, and the output signal, when the input is 0.1, the output has to be 1, right? So that's about a 10 times gain approximately is what is required. So based on that, find the required values of VOV, I, RD, and WL. Assume that the technology has this K and the early voltage is 0. Lambda is 0. So this is the condition. Here are the other formulas. And to see how all this is used, let's look at 8.14. Maximum VID has to be 0.1. That's input voltage, input signal voltage. Now maximum VID also has to be limited by another formula, another condition. So based on this condition, you can pick VOV to be 0.25. GM is this. So GM comes out. So GM is given, I think, as 2 milli. So I comes out to be 0.5 milliamps. Gain is output voltage by signal, which is 1 by 0.1 is 10. Gain is also has another formula. ROS can be taken as 0, so AD is GMRD. And based on that, RD comes out to be 5 kilo ohms. Lastly, using this formula, we can find the corresponding W by L to be 40. Okay, so that answers all the questions, all the required data we have found, and I hope it's clear. All right, let's move on to the next problem. Sorry, The previous one was problem 814 from the back of the chapter. The next one is 817 from the back of the chapter. There's also a kind of a design problem. So we have an NMOS employing two drain resistors, each of 47K, the differential voltage gain of 20. What is the value of GM? If each of the two transistors is operating at an overdrive voltage of 0.2, what must be the value of I? If input D differential is 0, what is the DC voltage across each RD? So that means only the common mode voltage applies. Next, if VID has a peak 20 millivolts peak to peak signal applied, sine wave applied, but that is superimposed on a VCM of 0.5 volts, what is the peak of the sine wave signal at each drain? Now 20 millivolts peak to peak means 10 millivolts peak, which is what's applied here. So we need to find the peak on the output side also. Okay. Sorry about my speaker symbol. Okay, it went away. Lastly, what is the lowest value that VDD must have to ensure saturation mode for Q1 and Q2 at all times, assuming a VT of 0.5. Okay. All right. So lots of things to find here. Let's go step by step and let's see how we did 817. So AD, the differential gain is given to be 20, which is also GMRD. So we can find GM as this. Next, using GM in this formula, with I can be found, and it's 0.085 milliamps because VOV is given. DC voltage across each RD is I by 2 into R with no input signal. It's just IR, right? So that is 2 volts across each RD. Now if VID is 20 millivolts peak to peak, then the formula for VD1 is half times gain times VID. Why are we taking half? Because VD1 or VD2 is a single-ended output, not the differential output, right? That's why we take half of AD. Half of AD is the total gain. So VDI is 20 by 2 into 20 millivolts, which is 200 millivolts peak to peak. VD1 equals VD2 peak is half of this 200, right? Which is 100, which is 0.1 volts peak. That is the single-ended output voltage with an applied input of 200 or 20 millivolts peak to peak. So 20 has gone up to 100. So there is a decent amplification. Minimum voltage at each drain will be VD minimum is this minus V peak, right? So that comes out to be VDD minus 0.21. For the transistor to remain in saturation, VD minimum has to be greater than or equal to VG max minus VTN, where VG max itself is V common mode plus V peak. That's the voltage at each of the gates. Or VG max is 0.5 plus 10 millivolts by 2, because common mode is given to be 0.5, right? Yeah, superimposed on a common mode voltage of 0.5. Thus, VDD can be calculated to be greater than or equal to 2.105 volts. Okay. So I hope it was clear how we went through each step. Here is the important formula we began with. For a single-ended output, the gain is half of the regular gain, the differential gain, and the differential gain is given, so we were able to fill in the rest. Okay. So these problems are not too difficult, definitely. They are pretty much straight applications of some of the stuff uh, we have already seen. So I hope these are not too difficult for you. All right, example 8.2 on page 602 is just actually a derivation, right? So we have this formula or this circuit, and we have these source resistances which are connected in this way. And then there is a load resistance here, RL, right? So if you have to include the source resistance, then the question is, determine the differential voltage gain AD equals VOD divided by VID, VOD here. And the differential gain comes out to be, it actually has RL also in the uh, formula, which is a little surprising. But he says first draw the half circuit. So see how you draw the half circuit. This RL is split in two. So you take only RL by 2 into consideration. Okay. All right. I'll let you look through the rest of it. I mean, it's not too difficult or too complicated. And I'm sure you can figure out the rest of it in the textbook. Okay. All right. Let's move ahead. Look at another exercise. This time we have a current source load, right? So the exercise is 8.5 from page 604. The answers are here. Let's read what the problem is asking. So the differential amplifier is fabricated and we are given the K parameters. There's a match set. This and this, I guess, are matched because mu n COX is 4 times mu p COX, which is 400. Vt is given, Va prime is given, bias current is given, and all transistors have a channel length twice the minimum. So this 0.18 micrometer is considered the minimum. So the channel length is twice, so that's 0.36. And they all have a VOV of 0.2 volts. So given all this, find W by L for Q1, Q2, which is the basic differential pair, and the current source loads are the PMOSs here. Okay. Also find the differential voltage gain AD. Okay. All right. Let's look. Hold on one sec. Okay. I'm going to open exercise 8.5 here. I don't know why I keep getting that transistor or speaker signal symbol. All right. So we are given I. and this flows through, it's the currents, the bias current source value, and that splits into two. So ID equals I by 2 equals 100 microamps in all of them, right? Half of it here, half of it here. So it's 100 micro in each. Now L is given as 2 times minimum or 2 times 0.18 micro. That's 0.36 micro. Because it's all matched, RO1 equals RO2 equals RO3 equals RO4. These are the intrinsic resistances of these devices, output resistances, and that's, each of them is VA prime times L divided by ID. So that's 10 volts into this divided by 0.1 milliamps, which is 36K, right? So that was that one of the questions? No, I think we need that RO to find AD, because there's no RDs, right? There's no drain resistors. So the formula to use is GM for each of the devices times the RO1 in parallel with RO2. That's why we need to calculate these ROs. Now, for the NMOS differential amplifier, which is the bottom two transistors, ID1 equals ID2 is this formula with the VOV, and the W by L is now for the 1 and 2 transistors. So using this formula, you can calculate W by L. Here you use mu n COX of 400. Here for PMOS, you use mu n COX of 100, right? Or sorry, mu p COX of 100. But the formula is the same, and you can find W by L for 3, 4, which are these two PMOS devices, to be 50. So the W by L is 50 here, and W by L is 12.5 here. So always remember the PMOS area is 4 times because it's a match set, and we know that mu n is always 4 times mu p. Finally, GM, you use this formula ID by VOV by 2, which is 1 milliamps per volt, and so you get the final gain to be 18 volts per volts when you use this formula. So I haven't listed those formulas, sorry, but they are in my notes. All right, let's move on. Now we have a cascode situation. Previous example was just current source load. Now we have current source load and cascoding. Cascoding is both on the differential pair transistors. So Q1 has Q3, Q2 has Q4. Also on the current source load. So Q7, it has Q5 as the cascode, and Q8, it has Q6 as the cascode. So design the cascode amplifier to obtain a differential gain of 500. Oh wow, so the differential gain we are seeking here is pretty high. Use VOV as 0.2, let VDD equals minus VSS is 0.9. So this VDD and the VSS at the bottom here, they are the same. And then we are given some other stuff. So you have to find the required channel length L. If GM is to be as high as possible, but the power dissipation in the amplifier in equilibrium is to be limited to 0.5 millivolts, what bias currents I would you use? So they brought in the power, which is generally voltage into current. So given the power, what should be the I? So that is the question. Now there is one uh, um, formula that we have talked about. I think I've shown that in the previous slide, which is this. Assuming in a cascade differential set, it's matched and they are all operating at the same VOV and they have the same um, early voltage parameter, then the gain is a simple formula given by this. And so that formula repeats here, and we're going to use that formula to solve this problem. Okay? All right, 826. So the gain using this formula, 500 equals this, which gives you VA, the early voltage, as 3.16. Now VA is connected to VA prime by this, and I think we are given VA prime. Yeah, VA prime is 5. So L then becomes this 3.6 by 5, which is 0.632 directly in micrometers. So that gives you L. Now the part B of the problem is how to find I, right? So I is P, power is VI. So I is power by V. Power is 0.5 milliwatts. What is the applied voltage across this whole thing? So the applied voltage is the voltage at the top minus the voltage at the bottom, right? So that's a positive 0.9. This is a minus 0.9. So if you take the minus, it actually becomes a plus on the denominator. So it's 0.5 divided by 1.8. That gives you 0.28 milliamps as the bias current here. Okay. So that wasn't too difficult, I think, a problem. Let's see how many more we've got. I'm skipping ahead. Slides 40, 41, 42. Okay, so we have an example on common mode, which is on page 611. Then there is a problem on common mode, 8.28. Two problems, I think. Yeah, and then we have the BJT example. All right. Okay, so example 8.3 is an application of the ideas of the CMRR, common mode rejection ratio. Only one mismatch is given, which is the Q1, Q2, GM or W by L mismatch, right? Not the other mismatch, the RD mismatch. So the formula, as we have seen here, is this formula that you use for GM mismatch. So I can actually copy it here. So you can see that this is the important formula. Now to be able to use this, you obviously need to find many things that are not given. Well, CMRR is given. It has to be 100 decibels, 100 dB, which corresponds to something in absolute value. That absolute value he finds, then he substitutes it, and he finds GM. He also finds RSS. So I'll let you look through it. I think the example is well done. It goes through step by step. And towards the end, the two questions that are important to ask is, I guess it's all about the channel length, right? Find L. That is the most important thing. And if only a simple current source is utilized for L, what channel length is required? And then if a cascade current source is utilized, what channel length is required? And you can see that the channel length in this first case is very high. That means the amount of silicon will be much higher. And if you want to bring that down to a reasonable value, then you have to use the cascading. Okay. So all this are in the steps in the textbook, page 611. I will let you look through it. I don't think it's all that difficult. It's interesting that a 2% mismatch in the W by L ratio, you can see how he converts that to a mismatch. How converts that to use in this formula. So take a look, and if you have any questions, we can discuss it. I'm going to move on to the next problem, which is 8.8. This is a PMOS version of the differential pair, and we had studied this earlier. I think problem 8.2 from the back of the chapter. We looked at it earlier too, but there we didn't focus on small signal or CMRR. Now we are going to do that. So here Q1 and Q2, they're both the same PMOS devices. So they have this K, and assume that the bias current source, this source, has an output resistance of 30 kilo ohms. Okay. The drain resistances are known to be 4K nominally, but there is a mismatch of 2%. VTP was given previously, I think, as minus 0.8. This is minus because these are PMOS devices. So using this information, find VOV, GM, AD, ACM, and once you know AD and ACM, you can take the ratio to find CMRR in dB when the output is taken differentially. Okay. All right. So let's look at 828. Yeah, here it is. So the currents will be half of this source current. The currents in the drains will be half of the source. That's 0.25. So 0.25 is also this formula from which you can find VOV. Once you have VOV, you can find GM to be this ratio, which is 1.416. The differential gain is GM times RD. Simple, because there is no output resistance to worry about. RO is not given. So that comes out to be 5.67. Common mode gain, on the other hand, is a definite value because of the difference or the mismatch, that's the word for it, mismatch of the resistance in the drain circuits. So 2% means this ratio delta RD by RD is 0.02. So make sure you understand what 2% becomes in the formula. The rest of it we are given. This is 4K. RSS, so he does talk about that. Remember, the bias current source has an output resistance of 30K. So this 30K is the RSS you use in this formula. Okay. So then ACM comes out to be a very low value. It's not too high, but it's definitely not, I mean, it's not too low. It's not zero, but it has some value. Hence, CMRR is 20 log AD by ACM, which comes out to be 72.6 dB. Okay. All right. I don't know. I guess, yeah. I think it's a pretty straightforward example. Nothing too concerning. Notice how we went step by step to find all of these, and then we found CMRR. Okay. Problem 831 next. So a MOS differential amplifier using a simple current source to provide the bias current is found to have a CMRR of 60 dB. If it is required to raise the CMRR to 100 dB by adding a cascode transistor, what must be the intrinsic gain AO of the cascode transistor B? So you have to pick a cascode transistor to go with the current source, and so we need to find the intrinsic gain AO. Remember, AO is just output voltage by input voltage without the load. I think, yeah, that's what it is. So what should that be? If the cascode transistor is operated at a VOV of 2.2 volts, what must its early voltage be, VA? If for the specific technology utilized, VA prime is given. So once you know VA, you know that VA and VAL are connected through that formula, VA equals VA prime times L. And you can easily find the L of the transistor. Okay, so let's see how to do 8.31. Cascode transistor has to be used to raise CMRR from 60 decibel to 100 decibel. Basically, that's why you want the cascode transistor. So the delta in the CMRR has to be 40 dB. What does 40 dB mean in terms of absolute number? It's 100. So the differential gain of the cascoding transistor has to be 100, right? If you use that 100, then your overall CMRR will go up from 60 to 100. So the differential gain of the cascading transistor has to be 100, which means AO has to be 100, which is GMRO, which is 2VA by VOV. So 100 equals 2VA by 0.2. So VA equals 10 volts. Straightforward, right? And once you know VA and VA prime is given as 5, L becomes 2 micrometers. Okay? I hope that was not too difficult. One second. Okay. That's it for these problems. I guess the only thing I have left then is to look at example 8.4 in page 626. This is in the textbook, so I guess I don't have to spend too much time on this. But the one thing that I thought was interesting, just the way the circuit is drawn, we always think that we will apply the input voltage, half of it here and the other half here, right? And we, in the formula, for the input, we use VCM plus half input, and here we use VCM minus half input, right? So let me show you what I mean. I have to go backwards a little. Yeah, sorry, not this one. Yeah, in this example, for example, figure 811, you see how the input is applied, VCM plus VID by 2 and VCM minus VID by 2, right? And you may be wondering how this is achieved. And so when I saw this last slide, I'm back on slide 47, this shows you clearly how you can do that, right? How you can take one signal source, which is in this case V signal, and you split it in two so that half of it goes in here with a plus sign and the other half goes in here with a minus sign. So that was the one interesting. Other than that, I'm gonna let you look through this example by yourself. We have two NPN devices. Every lot of data is given, the collector resistances, the VGD, there's a emitter resistance. Oh, sorry, these are the emitter resistances. This is just the resistance of the current source. So this is used in the formula here, right? And then we have the signal source, V signal, has its own 5K and 5K split into, 10K actually split into two. And then the emitter resistance are given. So a lot of things are given. You just have to find the input differential resistance RID, overall differential voltage gain VOD by Vsig, which is actually split into two, I think, in how he solves it. The worst case common mode gain, if the two collector resistance accurate to within 1 plus or 1 minus 1%, find the CMRR, use this formula, AD, ACM, and this is 1%, remember? And then the input common mode resistance. So all these have formulas, and they are all applied one after the other, and you can see for yourself how he proceeds to answer each of these A, B, C, D, E. I don't have any more questions on BJTs, but I may ask you one or two small questions here and there. But you don't have to do BJT problems in the quiz or here in the homework. Okay, so with that we finish 8.2 and 8.3. Next week we'll look at two more topics on multi-stage amplifiers from this chapter. Okay, all right, I'm gonna give you 1.5 minutes of your time back, which I keep stealing from, I've stolen already in other recordings. Okay, bye.